Hello class! Today we are going to explore an advanced techniques that helps machine learning models recognize objects they have never seen before. Now, how does this all happen? Let's say we have a model that has learned to classify cats, dogs, and horses, and then encounters a lion for the first time. It can still recognize the lion based on shared attributes such as has fur, has 4 legs, and belongs to the feline family. By relating these attributes to what it already knows, the model can make an educated guess. This is what is called zero-shot learning. In zero-shot learning, a model is trained on a set of known classes called seen classes, and then asked to classify unseen classes that were not part of the training set. It does it through semantic attributes, which are descriptive properties that help define objects. However, traditional zero-shot learning is highly idealistic because it assumes that the model only has to classify unseen categories. In the real world, AI system must identify both seen and unseen categories at the same time, which brings us to the concept of generalized zero-shot learning. Unlike zero-shot learning, which tests the model only on unseen classes, generalized zero-shot learning requires the model to classify both seen and unseen categories simultaneously. This makes the problem significantly harder because models tend to favor seen classes. For example, if a model has been trained on a large dataset of dogs but has never seen lions, it may incorrectly classify a lion as a dog simply because it has never encountered lions before. The biggest challenge in generalized zero-shot learning is reducing bias towards seen classes while still correctly identifying new ones. So, how can AI overcome this problem? It's called generative models for generalized zero-shot learning. It's a mouthful, but let me explain. One of the most effective ways to tackle generalized zero-shot learning is by generating synthetic training data for unseen classes. Instead of relying solely on attribute-based reasoning, we can teach the model what unseen categories might look like by generating realistic examples. This is where generative adversarial networks, GANs, and variational encoders, VAEs, come in. These models synthesize new training samples, helping the AI develop a better understanding of unseen categories. Why use WGAN instead of vanilla GANs? Because regular GANs often suffer from training instability, making it difficult to generate high-quality images. WGANs instead improve upon this by providing smoother and more reliable training, reducing instability issues, generating higher quality synthetic samples, ensuring unseen classes look more realistic, and reducing bias towards seen categories, helping the model generalize better. The key idea behind WGANs is to make training more stable and the generated data more representative of real-world distributions. This significantly improves a generalized zero-shot learning model's ability to recognize both seen and unseen objects with greater accuracy. Let's look at the big picture again. Traditional zero-shot learning is unrealistic because real-world AI needs to classify both seen and unseen objects. Generalized zero-shot learning provides a more practical approach, but it introduces the challenges of reducing biases towards seen categories. Generative models like GANs and VAs help bridge this gap by creating synthetic training data for unseen categories. WGANs improve the process by making training more stable and the generated data more useful. By leveraging these techniques, generalized zero-shot learning enables AI models to become more adaptive, flexible, and capable of recognizing new objects in real-world applications. This topic represents an important step towards building more generalizable AI systems, allowing them to classify novel objects with minimal supervision while maintaining high accuracy across both seen and unseen categories.